Okay, now let's take another look at the universal law of gravitation and try to use it to understand this concept of gravitational fields. So let's take the Earth and let's take someone standing on the surface of the Earth or near the surface of the Earth. Earth has a certain radius, which is a well-known quantity. And let's try to figure out how to derive the acceleration due to gravity for an object near the surface of the Earth using Newton's theory of gravity. So we know based on observation that g on the Earth's surface is about negative 9.8 meters per second squared, or negative 9.8 meters per second squared, downward towards the surface of the Earth. So if we start with the universal law of gravitation, and we want to say, well, what's the force of gravity between the Earth and someone standing near the Earth? Well, that's going to be the gravitational constant times the mass of the person, let's call it MP, times the mass of the Earth, divided by, and if I'm near the surface of the Earth, then I'm just going to use the radius of the Earth from the center to the surface squared as my distance. Okay? All right, well, we also know from Newton's second law that net force equals mass times acceleration. And when the only force is Fg, that the net force is the force of gravity, and that measured acceleration is little g. So what I'm going to do here is substitute this in for Fg. So Fg becomes the mass of the person times the acceleration due to gravity. And then I have the same thing over on the right-hand side. And what you notice right away is the mass of the person gets canceled out. And I'm left with an expression, acceleration due to gravity is equal to g times the mass of the Earth over the radius of the Earth squared. And when I plug in the known values, so 6.67 times 10 to the minus 11th, and that is a Newton meter squared per kilogram squared. It's a constant of proportionality. The mass of the Earth, which is 5.98 times 10 to the 24th kg, massive number, if you think about that. And then the radius of the Earth, which is 6.37 times 10 to the 6th meters, but square that. When I calculate that all through, what I get is approximately 9.8. If I look at the units, I get 9.8 meters per second squared, which is exactly what I'd expect to get based upon what we've known from empirical observation, that we measure that to be 9.8 meters per second squared downward. Now we have a special name for this, because if you notice, this is independent of the mass of the person. So whatever I put near the surface of the Earth has the same acceleration due to gravity. So we call this the gravitational field strength. Be nice if I had the G there. So the gravitational field strength near the surface of the Earth. So this is independent of anything in it. And what it tells us, if we have an Earth something like this, because it's dependent upon the mass of the Earth, as the Earth gets bigger, the gravitational field strength would get bigger. But as I go farther away from the Earth, the gravitational field strength would get less. So I can draw this as a vector field. And a vector field is a representation of the strength of the gravitational field in the direction in which it's acting at any given point. So if I'm near the surface of the Earth, no matter where I am located, I'm going to feel a certain gravitational field, 9.8 meters per second squared, towards the center of the Earth. As I go farther away, that radius increases, the gravitational field strength is still pointing towards the center of the Earth, but it's getting weaker. And it's getting weaker because I'm at a greater radius distance from the center of the Earth as I go farther and farther. And even farther away, it's going to get smaller and smaller. So the gravitational field can be represented as a vector field that varies inversely with the square of the distance away from the center. So it gets smaller and smaller as I go farther away, but is always pointed towards the center of the Earth, and is independent of the strength or the mass of the person. Its strength is independent of the mass of whatever is within the gravitational field. So there's how we could derive the acceleration due to gravity and then represent it as the strength of Earth's gravitational field. So if you're solving a problem and it's asking about gravitational field strength, it's just asking about the value little g.